Swayam Prabha. Digital India. Educated India.
Hello and welcome to the medical image analysis course. This is one of the few introductory lectures about medical imaging systems in general, where you will get an idea of what the images produced by these imaging systems actually represent. Okay. So, these are the four imaging systems that we will look at: X-ray imaging or X-ray projection radiography and X-ray computer tomography, magnetic resonance imaging, ultrasound imaging systems, and radionuclide imaging. So, not necessarily in this order, but we will cover all these four to get an understanding of what the images produced by these systems actually represent, right, like I stated before. One of the things we will not do is to look deeply at the image reconstruction techniques. Okay. Some of them all, in fact, X-ray, computer tomography, MRI and radionuclide imaging all require some form of inversion technique to actually obtain the image. So, but we will not go delve into the details of such techniques. We will just look at how the image is actually acquired, and we will in passing note what the kind of formulation that is required to obtain the actual image from the signals that are gathered by these imaging systems. Okay, so first we will start off with the radiographic imaging systems, which is basically X-ray radiographs. These must be familiar to most people at some point in your life if you have had some form of a fracture, or maybe you had some chest complaints or respiratory complaints, and you would have done X-ray or projection radiography or chest X-ray in general. You should have most of you would have done. Okay, so we will start off with the basic components of a radiographic imaging system. Also look at what is the physics behind X-ray interactions with tissue and how images are acquired. Okay. So, X-ray, this is one of the oldest among the oldest imaging system modalities. So, X-rays in general were discovered in 1895 by Röntgen by experimenting with these cathode ray tubes or Crookes tubes, and X-rays are basically nothing but electromagnetic radiation, right. They are electromagnetic radiation, but with slightly higher energy. So, they occupy the high frequency range of the electromagnetic spectrum. Okay. So, if you look at the EM spectrum, so which is plotted here right from the photon down right here, I have indicated the type of radiation that most of you would be familiar with, and out here is the energy range, right. Energy range is stated in electron volts. You can look up and convert it into, let's say, joules or whatever system, or in fact into wavelengths if you are comfortable with dealing with wavelengths, right. So, infrared and visible, these are of the order of nanometers, right. So, as we move here to the X-ray range, the energy is of the order of thousands of electron volts, right. So, typically if you are trying to look at the medical X-rays, right, the ones that you use for imaging, they would be of the order of tens of kilovolts. So, tens of kilovolts, for instance, if you look at a X-ray computer tomography machine, you would have something of the order of 180 to 150 kV, right. So, these are some typical numbers. So, these translate to about 10 raised to 3 to 10 raised to 5 electron volts. This is the range in which the medical X-rays are typically used, right. A lot of the X-ray applications fall in this range. So, just for reference, if you are looking at visible light, that is basically VIBGYOR, that corresponds to 1 to 10 eV. Okay. So, that gives you the idea of the energy differences in between these two parts of the electromagnetic spectrum. So, this is one of the reasons also why X-rays are also kind of a safety issue, because they are slightly high energy, they can cause damage at the cellular level. So, there are a lot of safety procedures built in place to avoid overexposure when examining a patient. Okay. So, how are these X-rays produced in a modern X-ray tube, which is part of a X-ray radiograph imaging system, right. So, this is basically a vacuum tube which consists of a cathode. So, it has a, so the modern X-ray tube basically consists of a cathode, which is nothing, a filament of wire, which is shown right here. I want to mess up the drawing, just there. So, that cathode actually is the emitter of electrons, it is thermionic emission. So, if you pass current through it, it heats up and it emits electrons, right. And these electrons are accelerated by a potential difference, okay, across the tube and to hit something, the anode plate or the anode target. See, the anode target is typically coated with tungsten or other materials, with high Z materials, okay. So, as the electrons hit the cathode, they penetrate it, and in the process they emit energy. There are emissions in several forms, we will look at those later, and that the electrons are absorbed by the target anode, and the process by which they are absorbed results in the emission of X-rays, right. And there are primarily two different types of X-ray emissions. One is called characteristic X-ray, the other one is called the Bremsstrahlung. We will look at this, those two in detail in later slides. But this is the typical construction of an X-ray tube. Of course, the modern tubes have, there are all kinds of modifications have been made to enable much more efficient imaging. So, we will not discuss that too much, just to understand that this is how X-rays are produced. Of course, another point to note is that all these electrons that are emitted by the cathode, they are accelerated across a potential difference, and they are focused to hit a spot on the anode target, right. And this actually it's important because the spot, the size of the spot has an impact on the resolution of the image that is finally produced. So, in lot of the image reconstruction techniques, just to mention in passing here, you would make this idealization that it is actually a point, right. The X-rays come from a point. That is not necessarily the case. So, for instance, if you have a clinical X-ray tube, the spot size would be of the order of it is 0.5 millimeter, maybe 0.2 to 0.5 millimeters or even larger, okay. Because you can't make, if you want higher flux, you need a larger spot size. So, the focusing of the electrons onto a particular spot affects the resolution of the image, which is finally reconstructed. But again, we will not go in too much into detail here on just because we want to understand how these the images acquired, how these images are formed, and also just to understand what these images represent, right. So, this is a very slightly qualitative look at these imaging systems. Okay. So, like I mentioned, there are primarily two different mechanisms, right. So, we will go we will explain this graph later. I will come back to this one, but we just look at the Bremsstrahlung and the characteristic radiation. There are two different radiation that are typically emitted. So, just to point out here anyway, since we are on this slide, see, the Bremsstrahlung radiation would be basically these continuous things, right. Yeah, so, these flat regions, okay, and here similarly everywhere, right. So, these are the regions which correspond to the Bremsstrahlung. They are the continuous emissions. Okay, so, just in case you are wondering what the axis are, the y axis you can treat it like a number, right. So, the number of X-ray photons emitted, and the x axis is the energy, right. So, it is basically like a histogram of the number of photons emitted in each energy range, okay. And it's actually, you can normalize it so that the area under it is 1, etc., but typically that gives you like a you can treat this like a probability distribution of the number of the probability of an X-ray photon belonging to a particular energy. So, each point here, again if you look at this plot, so this is an energy and the corresponding point would be, how do I wipe this off, is there a way to, okay. So, if you draw a straight line, yeah, this point would correspond to the number or the probability of finding an X-ray photon with that particular energy, right. So, this is more like a histogram of the counts. So, if you count the number of photons according to energy and then you plot the histogram, and this is what it would look like. And so, these continuous portions correspond to Bremsstrahlung, and if you see these peaks are the characteristic. So, why is it called characteristic? Because they are unique to every material, okay. The material in this case we are looking at the target material, like we saw in the previous slide. If you remember, we had a target, this is the anode target, right. It is made of a certain material. So, for instance, I mentioned tungsten, okay. You can coat it with other things also, high Z materials or high atomic number materials, and the X-rays emitted will have a characteristic peak that will be different from this, right. This corresponds to, in this case, molybdenum, okay. The last one, this is the tungsten one, okay. So, there are the process of generating these peaks as well as the as the Bremsstrahlung is slightly different. We will briefly look at how these are produced. Okay. So, these both fall under both Bremsstrahlung and characteristic radiation, they fall under what is called radiative transfer. The other thing that occurs is collision transfer. So, we saw that in the way that X-rays are generated is that you have these electrons accelerated across a potential difference into the to strike the target, and once that happens, say the radiative transfer process leads to the X-ray emission. The other processes, which basically the electrons just collide and come to a halt or are absorbed by the material, and in that process a lot of heat is emitted. Okay. So, it basically goes away as heat, right. So, the characteristic radiation happens when if you are familiar with the Bohr model of the atom. Okay. If you are not familiar with the Bohr model of the atom, you can please look it up. So, the Bohr model of the atom puts these electrons around the nucleus of an atom in K, L and M shells, different shells. Each shell can have only a certain number of electrons. So, the characteristic radiation is produced when the incident electron collides with the K shell electron and knocks it out, right, and ionizes the atom. So, the K shell is then filled with electrons from L, M or N shell. Okay. These are high energy shells. And so, when this filling happens, so when K to L, when the L to K or M to K or N to K transitions happen, there is a loss of energy which is basically in the form of a X-ray photon. Okay. So, that is the characteristic peak that you would see in the spectrum, right. So, the difference in the difference in the energy, right, from going from K, L and M shell, right. So, for instance, L to K shell transition, M to K shell transition or N to K shell transition, it is unique for different elements. Okay. So, that is why these peaks are also characteristic of the atoms involved, which is basically the atoms of the target. Okay. So, hence the name characteristic radiation or characteristic peaks, which you will find in the X-ray spectrum that I showed earlier. Okay. Okay. So, the second dominant contribution or the most dominant contribution to the X-ray spectrum is basically the so called breaking radiation. This is a German word for breaking. So, the interaction, which is basically the interaction of electrons with the nucleus of the atom. Okay. So, how does it interact? Because as the electron approaches the nucleus of the atom is positively charged, right, it has protons in it. So, it will slow down the electron. So, it is something like a a satellite around a planet, right. So, it actually slows down the electron as it approaches the nucleus, because it pulls it in whichever trajectory it is in, it pulls it towards the nucleus, right. There could be some collisions can happen, right, because but then these are rare, right. But most electrons, what happens, it slows them down, but then and they do move away from the atom, but with lower energy, right. So, but there are theories and of course, experimentation also show that when a charged particle is decelerated or accelerated, then there is loss of energy in the form of radiation, which is what we observe with the rest of the spectrum. So, the continuous parts of the spectrum fall under this Bremsstrahlung or breaking radiation, which is emitted when the electrons that are striking the target are slowed down by the nuclei of the target atoms, okay, because they are positively charged, they will tend to slow them down and change their trajectory. So, slow down also means not necessarily they are basically accelerating. So, you either pull them away from the original trajectory, which leads to this emission of characteristic radiation. So, another point to note is that again once we go back to the spectrum, here one of the things you have to note, you see, is that the spectrum is a function of energy, right. You see, that is why it is called spectrum. So, whatever comes out from a typical X-ray tube has an entire range of energies, it is just not monochromatic. So, typically, but when you do a lot of the analysis or when you actually try to do reconstruction, etc., you would actually end up assuming like an average energy, or if it is just a monoenergetic beam, things of that sort. So, but that is not entirely true. So, you will have this range of energies, and this range is determined by the accelerating potential. So, we saw that as the electron is by thermionic emission, electrons are emitted from the cathode, but they are accelerated by a potential difference, right. That potential difference, usually stated as kVp, is what determines the maximum energy of the electron, okay, and that determines the maximum energy in the spectrum also. Okay. So, we will move on to what exactly, like I said, our idea is to understand what exactly is being imaged when we do radiography, right. So, what its images, what these images represent, at least well, for CT this is strictly true, but for radiographs this is basically the summation over these so called attenuation coefficients. So, these are called, this mu is called an attenuation coefficient. It is called a linear attenuation coefficient, okay. Linear attenuation coefficient. So, it has inverse length, that is the units. So, let us say it is usually in the form of centimeter minus 1 typically, or millimeters to the raised that is the unit. Okay. So, so what you have to understand is how do we, how do we perceive the human body or whatever tissue in terms of mu. Okay. So, mu is a function, is a very complex function, and it is a function of energy one. So, mu is a function of energy of the X-ray photon. Okay. It is also a function of the atomic number, right, and so depending on energy you will have yes. Okay. So, mu is a function of the energy as well as the atomic number. Okay. So, again it depends, it is a very complex function of that, and so and of course, this shows that it is a material property, its atomic number is Z. So, it is a material property, and the interaction between X-rays and materials, whether it be human tissue or any other material, is determined by this mu. Okay. So, the simple relation that typically is used to model this interaction between X-rays and material is, if you have, let us say, an incident beam of photon, X-ray photons, I0 is its intensity, okay, and through a slab of material which of characterized by mu, okay, and of course it is d centimeters thick, and if you measure the exit intensity of the X-ray photons, then you can write down the following relationship, right. In this case x, I have used x, sorry, it should be d. Okay. Okay. Now, this is true only if this is a homogeneous object, right. It is a just it consists of only one type of atom, nothing else, right. But a human body is not strictly not true, or generally most materials it is not true. So, mu is basically then a function of, right, or you can say in general any vector, we can just say it is a function of x, it is a vector, right. So, mu will change from location to location, right. So, then we can then write this relationship as okay. So, this is typically, but then there is one more thing that we are, one other assumption that we are making here, we are assuming that it is I naught and it is all at the same energy, some E naught, right. That is also not true. If you have a real source, then which means that if you want to actually count the number that comes out, then we just have to integrate it over the spectrum. We denote the spectrum by S of E prime, right, e raised to minus integral, then this is a function of E prime, right, and then we have to integrate over all energies. Okay, this will give you the number. Okay. So, this is the relationship that is typically used for all X-ray imaging modalities. For the case of radiographs, what we get is a super. Now, we know that for a radiograph, when we do a measurement, we just let us say measure I, then I is a superposition of all mu's, right. You can see that I is a superposition of all mu's, because the way to look at it is, if you take the negative log just minus mu d, or in this case if you just use this formula, then it is just my mu dx, integral mu dx, which means it is a linear superposition. So, that is why for an X-ray radiograph, all the structures in the human body are superimposed. So, that tells you why this is like a shadow, think of it like a shadow which you get with an X-ray. Okay. Again, many of these properties are dependent on energy. So, there is a certain energy range in which we get very good contrast. If you could put very high energy, there is a very good chance of course radiation damage, and also that sometimes our body will be transparent to some of these energies. Most of these photons will go through without interaction, and then you will not get any information. Okay. Okay. So, then what is this mu, where does this mu come from, right? We looked at this mu, mu is the linear attenuation coefficient. Where does this come from? Correct? That is a question. Where is what is the origin of mu? Or the mu originates from two interactions primarily, especially in the context of medical imaging X-rays or X-rays for medical use. Two things that two interactions that lead to this attenuation. So, one is called Compton scattering, right. So, okay, before you go into that, if you understand that mu is some way to describe how the X-ray photons are absorbed or scattered within the human body, that is all. It just represents a model for scattering. It is a mathematical model for how your measurements. You are firing some X-ray photons through some tissue, you are measuring the exit, and you want to know what happened in between, and this mu helps you just give a form a model. But on the physics basis is what I am going to look at. Okay. The Compton scattering has actually a bad impact on image quality. So, what it does is basically it is the incident X-ray photons interact with the outermost orbital, outermost shell electrons, okay, and that interaction leads to a deflection of the X-ray photons from its initial path. So, instead of going through a straight line, it just gets deflected. Again, remember these are all kind of stochastic in nature, in the sense it is not like you are following one photon at a time. Think of it in an average, millions of photons are coming through in a packet, some fraction of it will be deflected by this interaction. So, that is what you lead to loss of contrast. The photoelectric absorption, this is actually a desirable impact, because this actually gives you a very good high quality image, because the Compton scattering, because it is deflected, it will go and hit the detector at some other location if you are looking at 2D imaging, and that causes loss of contrast. Here what happens is that the incident radiation at k edge energies, we saw that, right, like for instance for a generation of X-rays also we saw that. The same way, if the incident X-ray, the diagnostic X-ray is higher than the k edge of some of the materials in the body, in a human body, then it is absorbed, leading to excitation of electrons. So, the photon is completely absorbed, X-ray photon is completely absorbed, and again this depends strongly on atomic number, and it diminishes with increase in photon energy. Okay. So, there is an actual relationship, I do not have the numbers with me at now, but Compton scattering is very constant, it's what can I say, it's a function of electron density, which is basically the atomic number. So, it is linearly on electron density, but over all energies it is constant. Okay. At higher energies, for a very high energies, photoelectric absorption does not happen. So, there just the photon just goes through. Okay. There are two other interactions which also occur, but are not very important for X-ray image generation, which is Rayleigh scattering and pair production. Okay. So, we will just now briefly look through some of the X-ray detectors or for projection radiography. Okay. We will just look at maybe two of them. I have given some notes about the other two. Welcome to look through those. So, the one that is used that most of you would have seen, either the storage phosphors or some kind of a screen film combination. So, basically what happens is you have a film, okay, which is light sensitive film, which is sandwiched between two scintillators, or these are two phosphors or two scintillators, right. So, what happens is when scintillator is something that converts your X-ray energy into light. So, that is why you have seen a cassette. If you go to if you done any imaging, you see they will have a cassette kind of thing, like a large plate. Will have this film sandwiched between two layers of scintillators, you can call it that, or phosphors as they are called. So, when the X-rays is incident on the scintillators or phosphors, then they are converted into light and they expose the film. Okay. So, this film again it can be of two types. One is they are instantly exposed and you can then digitize them. Okay. That is one way. The other one is called the photostimulable phosphors, wherein once it is exposed, the image is stored latently. So, then you have to once again excite them with laser and record the image as it appears. So, and basically when you stimulate them again with lasers, then there is some more emission of light which you can record and digitize. Okay. So, these are called PSPs, and here it allows for easy digitization. Okay. The last one, that is the most fast growing market, is the flat panel detectors, right. These are basically digital, fully digital systems where the detector is basically like has sensors which will directly convert your X-rays into a digital array of images. Okay. These could be charge coupled device cameras, thin film transistor or CMOS. CMOS is something that you see in your smartphone cameras, except that the CMOS will be coated with the scintillator material. So, when the X-rays hit the scintillators, they emit light and the CMOS array actually records that signal. Okay. So, there are again there is other ways of detecting X-rays, but these are the most common ways and people still use this techniques, right. Let me just go. Okay. So, here are some representative chest X-ray images taken from different publications. These are open access databases. So, this is what typical X-ray images look like. You might have seen some of them, but these are all chest X-rays. The top row is basically from a database called CHEX, but I haven't indicated what disease conditions they might have. This database has a large collection of X-rays with normal patients and patients with different kinds of respiratory problems or lung related diseases. The bottom row of images can correspond to people who have COVID. Again, this is once again from publicly from an open access journal paper. I have cited it below. Again, it shows different patients who have COVID conditions. Again, none of their identities are here. It just show a representative selection of images that you get from a projection radiography. Okay. So, we will now move on to X-ray, CT or computer tomography. Once again, again a most commonly used diagnostic imaging system, one of the most commonly used. Of course, X-ray projection radiography is some like the most common diagnostic scan that is done all over the world. That's the most common thing, right. People use it all the time, and this is again a fast growing imaging modality in the sense of the number of patients referred, etc. So, this once again the difference between this and what we saw for projection radiography is that this produces cross sectional images of the body, right. So, we saw that when you did projection radiography, you have a superposition of the anatomical structures. Primarily, if you look at the imaging equation, you will see that, but here with this we are able to get cross section. It is like if you have a patient lying down on the bed on a and you can slice the patient, right, and let us say the length of the patient is z axis, you can cut planes perpendicular to the z axis and you can look at them, right. So, those kind of images are produced by the X-ray computer tomography scanner. Here once again the images that are acquired, the signal that is acquired can still be considered projection. So, what is unique is that there is the inversion process, basically a mathematical technique called back projection or filtered back projection. There are other techniques also which take these projections and process them into a cross sectional image or stacks of cross sectional images, which will give you like a volumetric image of the entire body. Okay. So, here is the process. So, it is the same, the many of the the system is the same as what we saw for a X-ray projector. The X-ray tubes used in computer tomography and the X-ray detectors used in computer tomography are different from those, in the sense that these principles are the same, but they have slightly different materials, and the X-ray tubes in a computer tomography scanner are slightly higher energy ratings and have to be more robust because they are on continuously and they are pulsed. Okay. So, that is a difference. We will not go into details, but then the principle of X-ray generation remains the same no matter what kind of tube is there. Similar again same thing applies for the X-ray detection. Okay. So, using thin X-ray beam lines, right. So, we don't see, if you just look at the X-rays that come out of a X-ray tube, there is usually an exit window, it come out as like a cone. Okay. So, you can use the entire cone to actually capture images, okay. But typically there is a collimation which requires only a fan which captures the image. Okay. And using these thin X-ray beam lines, projections are measured. So, projection measurement is the same as what we saw for projection radiography, it is the same principle, but then you take the projections from different angles. Okay. So, let us say if you are done a chest X-ray before, you typically are required to stand in front of the detector, but instead think of you on a rotating table, of yourself on a rotating table, and then every time you rotate it by let us say half a degree, there is a projection image taken. Okay. So, that is the typical image acquisition process here. I will show you some images, at least an image which will tell you how, give you some indication how it is done. So, before this computer tomography came about, there were other efforts also to acquire cross sections, right, rather than just the projection, and they are known as axial tomography and linear tomography. I will not discuss them, just to just some historical perspective, right. Okay. So, X-ray CT detectors, once again we will just go through them quickly. This is again scintillator crystals with photodiodes, photodiode array. Okay. The scintillator once again is a material which converts X-rays into visible light. Photodiode receives the visible light to produce an electric current, which is what is recorded as your signal. Okay. And the scintillators are designed to have very high efficiency, in the sense they will capture most of the X-ray photons that hit them and convert them into a light, which are then measured by the photodiode. Okay. So, once again this the circuitry connected related to all this is again slightly complicated, because this acquisition has to be done very fast. Okay. So, they have very high end analog to digital converters, etc., which can digitize these signals very rapidly. Okay. There are other types of detectors also, which are now becoming more common, and of course, it is soon in the future that they will replace, hope to replace the existing systems. These are called photon counting detectors. So, these recent technological progress is basically when you are able to count photons based on their energy. So, typically most of the or all of the X-ray CT detectors are called energy integrating detectors. You can't differentiate the energy of the X-ray photon that hits it. So, basically it will hit the scintillator and you will get a bunch of light photons, which you will just which the photodiode will integrate, right. So, there is no idea of what was the energy of the incident photon, X-ray photon. So, now there is a way to know the energy of the incident X-ray photon, and those detectors use some materials like cadmium telluride and cadmium zinc telluride, which helps them to threshold and count. Yes. Again these detectors help. So, why does it help to have energy discriminating detectors in this case as or photon counting detectors? Because we saw that the attenuation coefficient is a function of energy. Okay. So, if we can reconstruct images based on photon counts, X-ray photon counts obtained at different energies, we can get different kinds of contrast. By contrast, what we mean is differentiation between different types of tissue. Okay, much better, because most of the human body is water. If you saw that mu, the attenuation coefficient, which is what is responsible for the it describes the X-ray interaction with tissue. If it's mostly water, then it's not too much of a difference, okay, density difference. So, the mu is not too different, except again maybe bones. Right, you can see that bones are very clearly shown in projection radiographs also, because they are much higher atomic number. But so this kind of detectors help you to get better contrast. So, you can reconstruct multiple energies and try to figure out different types of tissue, like maybe cancers become very obvious early on if you use this kind of imaging. But again, this is work in progress, right. Okay, so just wanted to promise, there are some pictures I wanted to show you. I hope the contrast is good. So, this is a cross section of X-ray CT machine that has been opened up, right. So, this whole donut like hole you see is where the patient bed goes in, the patient lying on the bed and the bed goes in through there. You see this piece, this T is this yeah, I do not know whether this color is visible, but yeah, that is your X-ray tube, it is slightly bigger than that, and this is the detector array. I do not know if you see it. Detector array, okay, and this other red marks just show the path of a X-ray from the X-ray tube to the detector array. So, those are the lines that we were talking about that you would measure. These are the lines that you would measure. Okay, there are different ways of doing this measurement, this projection measurement, especially for X-ray computer tomography. Something called parallel beam, fan beam, and cone beam measurements. There are different scanning configurations, right. These are scanning configurations to obtain projection measurements. Okay, then we will have to again process those projection measurements to get your final image. So, what are these? Before I go any further, these are actually, these pictures are taken from a text by Avinash Kak and Slaney. So, I will just mention that here. So, here we have, like I said, what do I mean by parallel projections, and what do I mean by fan beam projections, right. So, that is what we are looking at. So, parallel beams projection it was one of the earlier innovations, and so I am not used anymore. So, we will just focus on the fan beam. So, what it does is, so we saw that how we can treat the source of X-ray as a point, that is what it is here. So, this is the position of the X-ray, and it emanates a beam, fan beam, and when the cone of X-rays come out. So, you have collimated to like a thin fan, and this other outline here, if you can see it, that is, let us say, the human body or the object that you are trying to image. You have to make sure that the X-ray beam covers the entire object. This right here represents a representation of the detector array. So, you have a bunch of detectors here. You can think of each of these as some kind of a cell, right, that measures, that counts or measures, integrates the X-ray beam that hits them, right. So, this is how you collect lines of data. Right. So, this entire measurement, so if you can plot it, plot the intensity of the measured X-ray, right, as a function of position along this detector array. T is the position along the detector array, then you get this plot. So, this is called a projection, okay. And you can do this by rotating your X-ray beam and detector configuration around the patient, and for every angle theta with respect to the axis, let us say the x axis, you can collect these projection measurements, and if you stack them all up as a function of theta, like say one theta below the other, then you get a 2D image, you call that the sinogram, right. Sinogram. Collection of all the projections acquired at different angles, okay. And so its sinogram is basically, you can think of it as a function of theta and t. T is the distance along the detector array, theta is the angle with which you move. So, every angle, yes. Yeah, this we will get to reconstruction, yes, next step. Okay, so just to understand a little bit better, just this is a better picture of what you are looking at. So, what is here is a representation of the human torso somewhere near the thorax or chest, right. You can see that this is like the spine, you can see some lungs, etc. So, what we have to look at is just to understand physically that if you are, when you are looking at an X-ray beam, you have to think of it as having a finite dimension, because the detector has a finite dimension, the detector cells have a finite dimension. So, if you have a X-ray beam with let us say n, in this case n in is the number of photons incident on the patient, right, as if before you enter, that is if you count it, that is a number, and then of course, it passes through the body, let us say this is the length it travels through the body, right, it is written here, right there. So, and of course, this is the ray, that is basically the ray path, that is what is given here. So, this S, the length S is the length of the ray path, or it defines the vector that defines the ray path, right. So, you can always rotate your coordinate system so that x y is in this case y is along the ray path, that is not too hard to do. So, you can always do that, and all you have to do is integrate along that. So, your signal that you get at this one detector element is nothing but what is given in there is mu of x comma y, because that is in the plane along that path, so ds, okay, and that measurement that you get is basically log, this is equal to log of n in by what is measured at the detector nd, right, because we saw that, remember, if you, I wrote it with I, but typically the relationship would be n, the detector is n in exponential of minus integral mu ds, right, is that correct? Yes, okay. So, then if you do the math, it should be easier, from here you can get here, okay. So, what people do before reconstruction, we are not going to talk about the reconstruction itself, is that they do the log of the measurements. So, you need to have a reference detector where you measure the unattenuated beam. So, there will be one which you measure without anything in the field of view, you can measure, and you can use that to construct this, okay. In case if you do not know what is, because n in we do not know, right, because it is always attenuated beam that we measure. But you can always do a measurement a priori or have one or two detector cells outside of the field of view, so that you can get that number, okay. So, this is how projections are measured. I showed this because this is how projections are measured in a CT system, slightly different from what you would escape, because if you go back to that picture I showed you, see if you look, this is a bank of detectors right here in the yellow, right, and so it extends, so it has an xy area, right, and it extends along the z axis. So, these are finite sized detectors. So, they will catch a very small volume of the electron of the X-ray photon beam that you are getting, unlike the, and this is on a curved, it is on the circumference of a rotating gantry, these are curved arrays. You can also have a flat array also, and then the reconstruction algorithm is slightly different. So, once you have these projections at different angles, So, typically you would acquire slightly more than 180 degrees, okay. And depending on whether you are doing parallel beam acquisition, you can only need to do 0 to 180 degrees, because you see that after that it is redundant, 180 is the same as 0. For this fan beam, you have to acquire slightly more than that. But once they are acquired and you have this sinogram data, which is basically your projection as a function of your scan angle, your projection angle, they are typically reconstructed using filtered back projection, or there are many other techniques like iterative reconstruction techniques. There are some deep learning based techniques also which are done. And the CT image intensity is after reconstruction you get a CT image intensity, which is referred to as the Hounsfield unit. So, it is typically it is HU. Okay. So, how do you reconstruct? So, very quickly, again I am not going to walk through the specifics. Very simple way of looking at it is you take, so this is the projection. So, this is the projection data, right there. So, let us check, you take a point in the projection, right, some value, it has, this is some in this case this is indicated by q theta I is the angle of t, all my theta and q look the same, apologize. So, you take this point, but I will do the pre-processing later, I will just tell you how the reconstruction is done. Then you construct the grid. So, this box you see here is the image array or grid that you define, it is a digital array that you define, and what you do is you would take this point and smear it across the grid. What do you mean by smearing it across the grid is that, if you just for the sake of this particular argument, so there will be different image pixels at every point, right. So, this line will go through different image pixels that you are trying to reconstruct. So, wherever it cuts through an image pixel, you will assign the same value q theta I of t to that particular image pixel. So, you can do that from every angle and sum them all up. This q theta I t actually is called the filtered projection. So, what you will take is you will take the raw projection, which is your log data, right. You have taken this log nd over n if you remember from the previous slide, right, and you would filter this. There are many different types of filters, basically to remove the high frequency noises, or some of these spurious noises which can come, and as well as this filtering is essential because you are adding over all the projection. So, you need to that also helps, this filtering helps. So, it actually comes out of the derivation, but I will not go through that, but you have to take the raw projection, which is this log data, and you have to filter it. It is a digital filter. So, you use a fast Fourier transform to filter, and then take that filtered projection and back project. So, this is a typical algorithm. So, almost any maybe except for the deep learning techniques, pretty much every method will have this step somewhere where you have to by doing this smearing or back projection. Okay. So, once you do this, or after you reconstructed over all the, you do that for every angle, for every point on the projection, every angle. Once you have done this, then what you have, what are you reconstructing? You are reconstructing the mu, the map of mu for a certain cross section. So, to normalize it, to make it into CT, you would whatever you reconstruct, new reconstructed, I call it recon minus mu water, this number you would get for an average energy, because remember all mu's are functions of energy, divided by or mu r, and this is typically 0, but you will do that and you multiply that by 1000. This is what you call Hounsfield units. Okay. So, typically this number goes from minus 1000 to 3095. Okay. You typically add a offset of 1000, so it will go from 0 to 4095. If you recall, this is basically a 12-bit number. So, all the outputs from a CT scanner are 12 bits, but the values, so this difference why I spend some time here is because unlike the other two, we are going to talk about MR, we are going to talk about ultrasound, also going to talk about radionuclide imaging. Radionuclide, again there is some meaning, but for MR and ultrasound there is only relative contrast that is different. Here the absolute values actually have some meaning. So, if you scan somebody, for instance, let us say not somebody, let us say you take a what is called a phantom, these are objects that you create to scan in a CT scanner. You have like a glass of water, so plastic bag, you scan it in a scanner here, go to some other area, some other scan center and scan it, the values, the pixel values you will get will oscillate around 0, that is mu water, right, or 100 in this case, if there is noise it will be between 0 and 100. So, that value is fixed. So, it is an indication of mu, it is an average mu because your X-ray spectrum is polychromatic. If you have a monochromatic spectrum, then you will get exact value every time, you should ideally get. So, within the limits of noise, this mu should be same for different scanners. Typically bone gets a very high number, it will be more than 2000 or something typically. So, that again you can always reliably say anything in that area region is a very high density or a high Z material. Okay, these are some of the typical X-ray CT images. I have again given the source, the Radiopedia, and I won't go again. I am not a personal expert in anatomy, but still, this is the brain image. Okay, these two are images of the heart after injection of so called contrast agent. So, typically for some of the scans you would inject iodine, the high Z material, high atomic number material, which will preferably absorb X-rays. So, anything that absorbs more X-rays will show up as very bright in a X-ray CT scan, will have higher pixel value, which means that it corresponds to a higher attenuation coefficient. So, that will be shown there. So, there are other sections of images. So here these are the typical X-ray CT images. Again, one of the skull or the head I should say, and two from the heart. So, this just gives you an idea of what kind of contrast you should expect. Like I said, the Hounsfield units are restricted to a range minus 1000 to 3095 or 0 to 4095, typically 12-bit images like I mentioned, and these are grayscale images, there are no channels etc. like you would see for instance when you are using a camera or some other imaging systems, right. So, this concludes our description of X-ray radiography as well as X-ray computed tomography. The idea was to give you an idea of what what is involved in the image acquisition, what exactly we are imaging and what is the images represent. We saw that for the case of a projection radiograph, what we saw was a superposition of anatomies because we are summing through the attenuation coefficients through the body. For CT images, they are just a cross sectional maps of the X-ray attenuation coefficient which are obtained from a reconstruction algorithm. We did not go through the algorithm, but just gave you a general idea of what is done. Okay. So, we will move on to other imaging systems in the next class, hope to complete them and so that you get an idea of what each of these imaging modalities offer. Thank you.